All right, so let's see, we left off. Okay, let's take a good look at this one right here. Okay. So here was the graph, or the function. Okay, so it was y equals -1/2. That does a vertical flip, and it also makes the points shorter than they used to be. So it looks like it made it wider, but it didn't. It made it shorter, made the points less tall, if you want to think of it that way. Okay, this moves the graph left 3 units, and that moves it up 2 units. So we know where the vertex is, and then again, the pattern is we normally go over 1 and up 1 squared, over 2, up 2 squared, and so forth, and we do that on either side. That's why it has that nice symmetric shape. So if we normally from the vertex go over 1 unit and then down 1, we're going to go over and down 1/2. So that's where we got to the 1 1/2, so we wrote that as 3/2. Okay. If we normally go over 2 and down 4, I'm going to go down half that far, so I'm only going to go down 2, so that's going to put me right here. And then we label those points right there. Okay, now everything that we did last time, with the exception of just a couple problems, it was all parabolas, right? Just a reminder of stuff that you'd seen before. Okay, now we're going to look at some things that are just a little bit different. So are there any questions before we get started? Okay, so let's take a good look at this guy right here. So this is the one that we talked about. We graphed y equals the square root of x. Again, that's why it's so important to have those parent graphs memorized, those shapes memorized. This goes through 0, 0. Whoops, something a little less bold than that. Goes through 0, 0, goes through 1, 1, and goes through 4, 2. That's what the parent graph looks like. If we multiply the x by a negative and then take the square root, so that makes the shape. That square root, that's what makes the shape. That's what makes this sideways parabola shape. If we multiply the x by a negative, that changes all the x's. It makes what used to be negative, or excuse me, what used to be positive, negative, and vice versa. So we can now plug in a -4. Because if you plug in a -4, the first thing that happens to it is we make it the opposite of that. So that would be the square root of 4, which is 2. So it takes the graph that was going to the right and it makes it go to the left. It does what we call a horizontal flip. Okay? So y equals square root x. If I put a negative out in front here, that would be a vertical flip. And if I put it inside with the x, that is a horizontal flip. Yeah?
So if you plug in a positive number for x, does that just become invalid? Or?
It does. And that's why the domain on this one, remember, it used to be from 0 to infinity. It used to be all the positives. Now it's all the negatives. Negative infinity to 0. Yeah? Because if you plug in a 4, you multiply it by a negative, that'd be -4. Square root of -4 is not a real number. Okay? Not one we could graph on here. Good there? Okay, so let's take a look at this. What does the 2 do to the graph? Okay, it does kind of make it taller, but a better way to think of it is this. We're changing the x, okay? And any change you make to the x does the opposite of what you'd think, okay? So remember when we had these guys, where we had x plus 3 quantity squared, that moved it to the left? You would think that this would horizontally stretch it out. It doesn't. What it does is it horizontally shrinks it. So let's take a look at this. Here's the parent graph. So this is the parent graph. So this is 4, 2. And this is, that point there is 1, 1. And then, of course, 0, 0. But if I'm going to graph this, here's what happens. I take the x coordinates and I shrink those by a factor of 2, or in other words, I divide them by 2. So I normally go over 1 and up 1. I'm going to go over half as far. So that's going to put me right here. That's going to put me at 1/2, 1. Then I normally go over 4 and up 2. I'm going to go half as far in the x direction. Notice that what we're doing here is we're changing the x before the square root makes the shape. So what's half as far as 4? 2. So this point's going to be 2, 2. So the graph would look something like this. Now, Samantha said that it makes it look taller, makes the graph taller. Well, it kind of does, but the better way to think of it is, what we've done is we've slid these points halfway back toward the y-axis, okay? So the next most convenient point to graph on this one would be 9, 3. But we'd go half as far as 9. What's half as far as 9? 4.5 or 4.5. So the next point on the graph would be, we'll call it 9/2, 3. Okay? So that one got shrunk back this direction also. Okay? Huge difference between a horizontal shrink and a vertical stretch. Okay? We didn't make this point right here taller. What we did is we shrunk this one horizontally. Okay? Again, if you change the x before the function makes the shape, it kind of does the opposite of what you think it would do. Okay? All right, now, if this was really true, okay, if I wasn't lying to you, this point is on the graph. 9/2, 3 is on the graph. Let's just double check and make sure. Okay? And this is why it works the way it does. This is why this is a horizontal shrink. If I take this and I plug it in, so this would be square root of 2 times something. What am I plugging in for this point right here? 9/2, right? What's the very first, now 9/2 is an ugly point to plug in, but what's the first thing that happens to it? Yeah, I multiply it by 2 and they cancel out. So this is the square root of 9, which is 3. So that point is on the graph. First thing that happens when I plug in a 2. If you plug in a 2, you times it by 2. That's the square root of 4, and the square root of 4 is 2. First thing that happens with a half. Multiply it by 2. That would be 1. Square root of 1 is 1. Okay, so does everybody see that that actually works? Okay, little counterintuitive. You'd think that multiplying by 2 would horizontally stretch it out. It doesn't. It horizontally shrinks it. Yeah.
So I was wondering, is that kind of like the x plus 3 squared thing?
Uh-huh.
It moves it to the left instead of the right. So it's
Does the opposite of what you'd think.
So is that the same thing with like dividing and multiplying?
Mm-hmm. Yeah. Yep. Instead of multiplying by 2, it divided it by 2. Okay? All right. So let's see if we can figure this one out. 2 horizontally shrunk it. Guess what 1/4 does? Horizontally stretches it. Okay? So the normal graph looks like this. So this would be 1, 1. This would be 4, 2. 1, 1. So it would normally look like this. Okay, this is going to horizontally stretch it out. So we're still at 0, 0. Okay, now instead of going over 1 and up 1, we're going to go over 4 times as far. Well, what's 4 times as far as 1? 4. So we're going to go up 4 and up 1. For this next point, we normally go over 4 and up 2. We're going to go over 4 times as far as 4. So what would the next point be? 16, 2. So it would be way out here at 16, 2, and this was 4, 1. So it looks like this. Okay, notice how it's been horizontally stretched. We took these points and we stretched them way out there. Okay, made them way elongated, if you will. Does that make sense? Okay, let's just double check. If I want to check this point right here, 4, 1, first thing I do is I plug it in and I multiply it by 1/4. What's 1/4 of 4? 1. Square root of 1 is 1. So that point is on the graph. Does that make sense? Okay. Those changes inside there, they're kind of weird. They do the opposite of what you'd think. Okay. So if we multiply by a negative, that's a horizontal flip. Okay. And here, if we've got a function that makes a shape that we know, and we multiply the x by a number before the function makes that shape, okay, the graph is horizontally stretched or shrunk. And here's the weird part. Shrunk if it's greater than 1, stretched if it's between 0 and 1. Okay, so again, a horizontal change. If we change the x before the function makes the shape, it's going to be a horizontal change of some sort. Horizontal flip, horizontal stretch or shrink, something like that. Okay, any questions there? Okay, I want to take a quick look at these problems right here, and then I'll turn you loose. You can work on the assignment for a bit. I do want to get started on 3.5, at least have you think about that, and then we'll finish that up tomorrow. Okay? All right, let's see. This one right here. Is that going to be a horizontal change or a vertical change? It's vertical, okay? How come, Chase? Can you explain why? Okay, because it's not in there with the X. We make the shape, then we add something to it. So that's going to be a vertical change. That's going to move it up 2. Okay, what about this one? Horizontal or vertical? Horizontal, because we're changing the X. We're changing it in the X direction. Okay, what's it going to do to the graph? What's the plus 2 do to the graph? Okay, this is going to be left 2. So if we were to graph this, what shape is the absolute value again? It's a V shape, right? So we're going to take that V shape and we're going to move it up 2. So that vertex, that point right there, is going to be at 0, 2, and then we'd go over and up, and we could label a couple points on there. Pretty good with that? It didn't change the shape at all. All it did was take that shape, perfect 45 in and perfect 45 out, and moved it up, the whole shape up 2 units. Okay? This is going to move it to the left, so we're going to take that same shape and go 1, 2, like this. Okay? And you could label those points, right? The vertex here would be -2, 0. Is that all right? Okay, let's look at the next one. Write an equation for y equals x cubed if it's been vertically stretched by a factor of 4 and moved to the right 5 units. Vertically stretched by a factor of 4 and moved to the right. Now, vertically, that's got to be a change after it makes the shape, so outside the cubing, not with the x, and to the right. See, if we move it to the right, that's horizontal change, right? So you got to change the x. How do you move something to the right? Subtract 5. So would you go ahead and write down what you think the answer is for this? So y equals x cubed. We're going to take that shape and we're going to change it by stretching it by a factor of 4, vertically stretching it by a factor of 4, and moving it to the right 5 units. Okay, write down what you think is the way to do that. Check with your neighbor, see if you got the same thing. Chase, you're not going to check with your neighbor? Y equals, if we're going to make a horizontal change, we better put it in parentheses. It's cubing. I move it to the right by subtracting 5, and then I stretch it by a factor of 4 vertically by putting a 4 outside. Okay? Everybody good there? Okay. All right. Let's see. And this is easy to graph, right? No problems there? Okay. Would you go ahead and do these problems here? Get started on that. It's not too bad. I think toward the end, once you get to about in the 30s and toward the end there, then it gets a little bit more challenging, but not too much. So go ahead and get started. I'm going to give you about 10 minutes to work, and then I'm going to pass out 3.5. Okay? So go ahead and get started.
So I forgot my phone. I kind of want to say this might be it.
So that was here.
I think it is.
Okay. Okay.
Thank you.
Does everybody have their book?
Yeah, I do.
Anybody lost their book? Good. Any questions?
I think I might finish. Weird. 59. The graph illustrated. Use the graph of the path of the first step first graph to the following. What? Yes. Like I got on the question as soon as after asking, does anyone need it? Dang it. Yeah. So it's out. What are you talking about? As soon as you need help in a store, all the employees are like, gone.
No, I know. Let's do it. Oh, I sold it. Oh. Do the same thing. And you do the same this one. I know, but you grab that. The guy with the 3-year-old. That's so weird. No. Oh yeah, it would be. That's really good. But then I went over to the HCC. My mom must have taken us recently. Oh, yeah.
I like how we all talk together. I'm so worried.
No.
I used to like, I'm really kind of
Waiting for Oh, yeah. You notice. There's everybody else in this room notices. Right?
I got a question.
What?
I had a question since you walked out of the room. Yeah, it's bugging me about it.
Seriously.
Yeah, right as soon as you left, I was like, dang, how do I do this? With this and all these other functions, am I just supposed to write down? Oh my gosh. I've just been drawing lines. I feel dumb.
Uh-oh. Okay, if you would move back to your spot, I'm going to hand out the notes for the next section. And I just want to introduce a couple quick ideas. Okay, Hustle, let's go. Yeah.
This assignment isn't due today, or not today, it's due tomorrow, or
It's due on Wednesday, but when should you be done?
tomorrow?
Tomorrow, absolutely. Okay, Hustle.
I did all of it already.
Okay, listen up. I just want to get through enough of this. We'll do the easy stuff today, and then we'll get to the more interesting stuff tomorrow. So for those of you that up until now, it's like, I've seen these graphs before. I know how to transform a parabola. Some of the ones on 3.4 may be a little bit difficult, but overall, if this has been pretty easy for the first couple weeks, I would say you could say that 3.5 and forward is about where things start to change to stuff maybe that you haven't seen before. Okay? So there's a typo on this. I left off an F, but let's say that's the function right there. Okay, we already know what shape this is. If we plug in a 2, we get a 1/2. So we'd be about right there. So 2 comma 1/2. That is the function value. The function value is 1/2. If we plug in a -1, we get out a -1. Okay, so we're right there. If we plug in a 1/5, what does the reciprocal do to small numbers?
No, it makes it bigger.
Flips them over, makes them really big. So this point right here would be 1/5 comma 5. Okay, so the function value there is 5. And then it says graph and label this. So we've got that guy right there. Got this graph right here. We labeled a couple points on this, -1, -1. So just a quick review. Okay, that is the shape that it makes. It has a domain, it has a range, all of that stuff. A little weirder shape than you came across in 1010, right? Okay, so here's the interesting thing. So can I move on? Okay, the interesting thing is that what we're going to do now is we're going to take graphs or functions and we're going to put them together with other functions. Okay, and as it turns out, you can actually add, subtract, multiply, and divide functions to make new, more complicated functions. Isn't that lovely? We like things to be more complicated, don't we? Okay, but then if you learned the basics on regular functions that are pretty easy to work with, okay, we can take those basic building blocks and we can understand things that are more complicated. Because in your careers, you're not just going to be presented with a nice, easy problem out of a book. You're going to have to figure it out. So part of what's difficult about 1050 is we're not just learning math, we're learning a lot of thinking skills, a lot of problem solving skills, and that's what you're going to see in 3.5 and 3.6. Okay, and then that's it for chapter 3. Okay? So here's what we're going to do. We're going to take two fairly simple functions. One's just the square root function that we looked at earlier, okay, and then a linear function, 2x minus 8. And here's what we're going to do with them. And this first part is pretty easy. I'm going to make a more complicated function by adding f to g. So I literally have a new function that's the square root of x, that's f, plus 2x minus 8. Now, it might not be a bad idea to put that in parentheses to just emphasize I've got this first part, that's f, and this second part, that's g. I'm just adding the two of those together. If I put it in parentheses, I'm less likely to make mistakes down the road. Okay? Any questions? That's it. That's how you add the two functions together. Okay? So let's subtract them. Well, if adding is that easy, subtracting is about this easy. Everybody watch, please. Did I do that right? I did not. What did I do wrong? I didn't put it in parentheses, and that is a huge deal when you're subtracting, because that changes this to the square root of x minus 2x, and if I distribute that 2, this would be plus 8. Okay, that's not a big deal on this example right here, on A. It's a huge deal when we're subtracting. So, please put things in parentheses, especially when there's subtraction or there's some possibility of distributing things through. Okay? Which is what comes up next. Because this is f times g. So this is going to be the square root of x times 2x minus 8. And look at how different that would be if I left off the parentheses. It would look like the square root is only multiplied by the 2x, not the negative 8. Now, the great thing about this is you might want to leave it like that. That might be the answer. Or you might want to write 2x square root x minus 8 square root x. There may be a need for that. But either way, this is fine as long as it's got the parentheses on it. Good? Okay, now watch please. Okay, this function you can plug in anything you want as long as it's 0 or bigger. Anything but negatives. We call them non-negatives are okay to plug in here. Okay, what can you plug into this function? All real numbers, anything you want. Okay, so this has a pretty nice domain and this has a pretty nice domain. Now watch what happens. The minute I divide these, so this is what I get when I divide them. I have the square root of x divided by 2x minus 8. What were those three functions that have domain issues? Division by 0, even roots of negatives, and logs of negative or 0. Okay, this operation is one of those operations that creates domain issues. So even though we used to be able to plug in anything we want into 2x minus 8, there's a number we can't plug in now. What is it? You can't plug in a 4. So we'd have to say x not equal to 4. Okay, so you can't plug in a 4. And we also restricted the top two, 0 to infinity anyway. So this is our new domain. Oops, let me make that look a little better. Okay, so this is the hardest one to figure out. These others are pretty easy because you can plug in anything you want except for negatives. So the domain for this would be, 0 to infinity, square bracket. Same thing for this, 0 to infinity, square bracket. And same thing for this, 0 to infinity, square bracket. Okay? It's the smaller of the two. So if this one's negative infinity to infinity, if this one's all and this one's 0 to infinity, we just limit ourselves to the smaller of the two. Okay? Any questions there? Okay. And the only weird thing that was introduced is when we divided. Okay? So let's take a look at this next example here. So f of x is 3x plus 4. Plug in anything you want. G of x is x squared minus 3x plus 1. Plug in anything you want. What about this guy right here? Is there anything you can't plug into that one? Okay, so that's the only one that has a domain issue. So if I take f and I subtract g, that's going to be 3x minus, what do I need here? X squared minus 3x plus 1, right? And then if I were going to distribute and simplify, 3x minus x squared plus 3x minus 1. And I'd put these together so I'd have negative x squared. That would be a plus 6x and a minus 1 if I were going to simplify that all. Oh, I'm sorry. Plus 4. So this would be plus 4 plus 1. So this is going to be a plus 3. Is that right? Does that sound good? Okay, thank you. It is Monday morning. Okay. Good there? Okay. F plus G, or sorry, F plus H. I'll try and get it all right here. 3x plus 4 plus H is x over x minus 3. Now, do you think we want to do any simplification here? No? Okay. This is fine right here, but let's go back and let's talk about the domain for each of these. You could plug in anything you want into this one and anything you want into this one. So guess what the domain is here? All real numbers. So this is going to be negative infinity to infinity. Okay, you can plug in anything you want in this one, but there's one number you can't plug in here. So guess what the domain is for the whole thing? Yep. You can plug in anything you want, negative infinity to infinity, as long as it's not equal to 3. Okay? Again, we kind of take the smaller of the two domains. Okay? And we're almost done, at least what I want to look at today. This one says take f and divide it by h. So that's going to be 3x plus 4 over x minus 3. Now this one might take a little bit of thought. Let me change colors here just to kind of keep this uniform. 3x plus 4. What can you plug in there? Anything you want. X over x minus 3. What can you not plug in here? Okay, so does everybody agree we're going to have to throw out 3, at least? Okay, now let's simplify and watch. I'm going to flip that over. So that's going to be x minus 3 over x. So if I simplify this, I have 3x plus 4 times x minus 3 over x. Now take a good look at that. Is there another number I can't plug in? Can't plug in a 0. So I also have to throw out 0. Does that make sense? Okay, here's why. If you look at what you started with, you can't plug in a 3. So everybody's okay with that, right? Well, you can plug in a 0. You get 0 over negative 3, so the answer to this is 0. But guess where that ends up? It ends up in the entire denominator. So that would be 3x plus 4 divided by 0, and we know that part's not okay. That's where this extra number comes in. the 3 because of the division in the original problem, and the 0 because of the division that we introduced right here. Does that make sense? So you've got to be aware of all the domain issues that come up as we put these functions together. Okay? Let that cook in your brain for a little bit. We'll finish up 3.5 tomorrow. Have a great day.